Hello everyone, welcome back to another video related to electronics. This video is the second part of a previous one related to bipolar transistor. In this occasion, I'm going to cover one of the working modes of this device, which is saturation. As usual in my videos, you can navigate through them. In this video, you are going to find three parts. In the first one, I'm going to give you all the tips and hints that you need to know in order to understand the theoretical context behind the saturation mode. In the second part, I'm going to cover a full numerical example of a transistor working in this mode. Finally, in the third one, I'm going to take all these components from the numerical example and I'm going to mount it in a breadboard. And then we are going to compare results, so from theoretical and also from experimental results. So without further ado, let's go started. Okay, so let's go back to our blackboard. If you remember from my previous video related to bipolar transistor, we covered two of the working modes of this device, cut off and active. I strongly recommend watching this video in case you haven't done yet. And right now I'm going to focus on the very special one, which is saturation. So remember the terminal of bipolar transistor. This is a NPN, and here we have a meter. Okay, meter, here is the base, and here is the collector. So if we talk about the ranges of voltages at the terminal of this transistor when this one works in the saturation, we will say that the lowest voltage is going to be at the meter. So because of that, I'm going to put here a minus, but and here is a big difference compared to active is that the most positive one is going to be the base, and then the collector is going to be less positive than the base. So as you can see here, so the union between base and emitter, which is the most important thing in a bipolar transistor. Remember, a bipolar transistor is a transistor activated by current. As long as you are able to activate the union between base and emitter in forward mode, so suddenly the transistor is going to start to work. So means current through the base, you are going to have current through the collector. All right, so what else? All right, so the thing that we are going to have now is that the current through the base is going to be different from zero. Then consequently, the voltage between base and emitter is going to be more or less 0.7 volt. And you have to take this voltage with a pinch of salt, because saturation is a mode where the thing that we are going to try to get is high current through the collector, and consequently you are going to have high current through the base. Because of that, and considering that this is a diode, the higher is the current through the diode, the higher is going to be the voltage drop between base and emitter. So it's very common to find voltages between base and emitter in saturation close to 1 volt. So far we are going to suppose that is 0.7. The second equation that we are going to use is the one that makes a relationship between the current through the collector and the current through the base. And that is done by this beta, which is beta sat. Look that here the equation is almost the same. The only thing that is going to change is beta sat. Beta sat is a different beta from the one that is inactive, and this beta sat is going to be much smaller, okay, much more smaller than the beta for active, and it's usually in the range of 5 and 20, and it's something that the designer is going to force, okay, this beta. We are going to see that with more count during the numerical example that I have prepared. Before keep on going with the last equation that we are going to use in saturation, let me remind you that the beta sat also you are going to find in the literature, okay, as force beta. And now, yes, the last equation when you are in saturation that you can apply is that the voltage between collector and emitter is going to be around 0.2 volt. Again, this voltage should be taken with a pinch of salt, because only when you have enough current through the collector, this one close to the nominal current of the bipolar transistor that you are using, okay, you are going to achieve this voltage. Otherwise, this voltage is going to be much, much smaller. So if you are in saturation because you think that the arrangement of voltages through the terminal is going to be the one that you have here, you can apply these three equations, okay? And finally, the thing that you have to ensure is that the voltage between collector and base is smaller than 0, so it is negative, okay? So now that we know all the equation and other theoretical concepts, let's go to dive into a numerical example. Right, here we have our circuit where we have a bipolar junction transistor, which is a NPN type. Then we have DC sources, voltage sources, that it's this one, 12 volt, that is going to provide current through the collector and is going to activate this load that we have here. And then another one of 5 volt that is going to provide current through the base and is going to activate the bipolar transistor. Look at the resistance that we have here, the resistors that we have. So this one that is 120 and that one that is 80. If you compare to the previous video where I covered active, the value of a resistor was in the range of kilo ohms, okay? Because this one is much smaller, so the current through is going to be higher. Typically in saturation, the current through the collector is going to move between 0.1 amp, okay, to 10 amps, depending on the application. So that means also that through the base, we move between milliamps and hundreds of milliamps. What else? So data that is going to be given, in this case, beta force 8. As I told you, very small. In case that is saturation, then the voltage between base and emitter, 0.7, and the voltage between collector and emitter, 0.2, the standard one. Let's go now to apply, okay, these equations and to find voltages and current through the terminals. First thing that we are going to do, it's to suppose that we work in saturation, okay? And before keep on going, let me remind you that this analogy that I had with the highway. So this is a highway, a junction, and remember that I mentioned before that is going to be the base, that is going to be the collector. Here, the union of the junction is going to be the emitter. So as long as the electron that come from here and is going to be incorporated at the highway are able to pay the toll, okay, so it's going to be created, the current through the base is going to be created. This small current is going to generate a big one, okay, through the collector. So the current through the collector is going to be generated. So the current through the emitter is going to be the sum of both. Right, so let's go to focus through the base and emitter. And if we take a look to our circuit, here it's 0 volt. But the electrons, because we suppose that is in saturation, so the transistor is working, is activated, so you have current through, the electron were able to pass. But here you don't have any money at the pocket, so they had just the enough money to pass the toll. Okay, so that means that here the thing that we have is 0.7 volt. This is the minimum that they need to pass through this toll, okay? There is more ways, okay, to figure it out, okay, what is the voltage at the base, to reckon that. Another one, it's voltage base emitter. We know that this is 0.7, but at the same time, voltage base emitter is voltage at the base less voltage at the emitter. But look, this is the emitter, and the emitter is connected to ground, okay, so that means that it's going to be cancelled. Finally, the thing that we got is voltage at the base is 0.7, okay? Right, so now the electrons also has to pass another toll. That is the one given by the LED, okay? So the voltage drop across the LED, a red one, is going to move from 1.8 and 2.2. In this case, let's suppose that that is going to be the voltage through the LED is going to be 2 volt, okay? So means that 2 volt now apply there. So again, you have, okay, before passing, you got more money in your pocket, so more voltage. Now is the moment. It's the moment to compute the current through the base. The current through the base now can be computed, and that is going to be, remember, voltage at the beginning, that of the arrow is going to be 5, less voltage at the end, okay, is going to be 2.7, divided into the resistance that you have in the middle, and that is 120. If you do so, that is around 19 milliamps. Once we have the current through the base, we can apply this equation that we have here, and we can compute the current through the collector, which is going to be beta sat multiplied by the current through the base. So that is going to be 80 multiplied by 19 milliamps, and that is 152 milliamps, which is more or less 0.15 okay, amps. Okay, so at this point it's important to summarize what values we know. So here we have all the voltages through the terminal and current through also. So voltage at the base, we know that is 0.7 volt. Current at the meter is 0 volt connected to ground. Voltage at the collector is something that still we don't know. We are going to find later. Current through the base is 19 milliamps, which is more or less 0.02 amps. Current through the collector is 0.15 amps. So the current through the meter, that is a sum of base and collector, is going to be 0.17 amps. The last one is that we need is to find is the voltage through the collector, but to do so we are going to use that equation, that data, voltage collector emitter. Voltage collector emitter is voltage at the collector less voltage at the emitter, but we know that this is 0.2. But again, voltage at the emitter is 0, and that is going to simplify everything because the voltage at the collector is going to be 0.2 volt. So 0.2 volt here, we know everything, and finally the thing that we have to do is to verify our initial hypothesis. To do so, we have to ensure that the voltage between collector and base is going to be negative. If I split that, this is voltage at the collector less voltage at the base, but voltage at the collector is 0.2 and less voltage at the base, that is 0.7, and this that is going to be 0.5 negative minus 0.5 voltage, so negative. So means that our initial hypothesis is correct, and we work in saturation. It's important also when you work in saturation to compute some power dissipation, especially in the transistor, but I will do that in another example. Let's go now to mount all of that in the breadboard and see how this circuit works. Let's go. Right, here we have our experimental setup. First, the transistor, the 2N3055. As you can see here, is much higher than the 2N2222 that we use for active, because this transistor is able to withstand more current. Maximum current for the transistor, I think that is in the range of 15 amps, so much higher than the 100 milliamps of this transistor. Something that is characteristic from this transistor is that the cover that you have here, the metallic cover, is going to play the role of a collector. Then underneath you have two more pins, the base and the meter. Also in this experimental setup, as usual, you have the 5 volt that is going to play the role of this voltage supply, and also the 12 volt that is going to play the role of this other. Okay. The load is interesting because the load, I put it a motor. Motors or something that is going to demand a lot of current is the typical thing that you are going to put in the collector when you are going to make work the bipolar transistor in the saturation. And then the thing that we also have, it's the multimeter. This one right now is measuring the voltage at the base, and here we have the current meter, that is so ammeter, that is going to measure the current through the base. At the base we have a switch, which is this one here, and this switch is this one, okay, that I'm going to press to turn it on, and the LED that also is there, and the resistor. So if I press, okay, as you can see, the motor start working, okay, and if I release, stop. So let's go for the measurement. So in this one, we have 0.7 at the base, just the same as we measure, and for current through the base, the thing that we have is 19.6 milliamp. We computed just 19. That's very close. Everything is very close to the values that we expect. Another interesting measure to take is the one that involves the current through the collector and also the voltage at the collector. Because always a measurement of the current in the laboratory for my study is something complicated, I'm going to do it here on the spot. So my ammeter right now is measuring the current through the base. So the first thing that I'm going to do is to identify the 5 volt, okay, that is going to, I'm going to remove here. I'm also going to remove this one, that's the 2 terminals from the ammeter. Now I'm going to close the circuit and I'm going to verify that the circuit, okay, works. If I press here, everything works. Of course, I don't have current because it's disconnected. Now, because I want to measure the current through the collector, the thing that I'm going to do is to break the circuit at the collector, and now I'm going to put in the middle, okay, I'm going to put the ammeter, and I have to close the circuit at the place that I broke before. Okay, if I can. Right. So, done, and let's go. Fantastic. So here we have, so the current now, it's around 150 milliamps, that it's the one that we computed before, a little bit less, just a little bit, okay. Another interesting thing is the voltage at the collector. I'm going to do it here on the spot. All the voltages are referred to ground. Ground is common for both voltage supplies, and look here, so it's 0.02. 0.02 volt, okay, it's something that is far away from the 0.2 volt. And that is because the current that we have right now passing through the transistor is very low. I mentioned that. So the lowest, only you are going to achieve a voltage at the collector around 0.2 if the current that you pass through the collector is close to the nominal current of the transistor. This transistor is thought for maximum of 15 amps, so far away, and because of that, you don't achieve 0.2. In the instead, the thing that you have is something much smaller. Okay. Right, so that's all from my part of this video related to saturation. I hope that you enjoyed it, and I hope to see you soon as well. Till next time, bye bye.